Welcome, everyone, to our Advanced OpenACC course. It's great to see you all here, bright and early here in California, and probably late evening for some of you out there. So we're really happy to see you here and enjoying the course, I hope. Thanks for joining the lecture today. Today is going to be our last lecture of the course. And my name is Julia Levitas. I'm a product manager at our Tesla group and will help with the class today. So we have changed the structure of the course a little bit since the last time. We decided to make the session today a little bit longer than usual. So it's going to be an hour and a half long, and we will be able to answer more questions today. So the long lecture today with 30 minutes for Q&A will replace the office hour next week. So today is the last session of the course, and we will definitely do more courses, and we'll keep you posted on their new announcements. So let's start with some logistics. So every session of the course will be recorded and available for you to review on our OpenACC course page. So again, to find it, you can just Google Advanced OpenACC course, and the first page in the search that will show up will be the page for the course. We'll be posting there all the recordings, all the Q&As, and the slides. So probably tomorrow you will be able to find those on the page. So all the lines are muted right now, so please submit your questions through the Q&A pod on the right-hand side or the bottom of the screen. We'll do our best to answer as many questions as we can today, especially if we have this long session. But also keep in mind, we do have an email address that you can send your questions to. It's openacc@nvidia.com. So that's a source that you can use for your help. We also monitor the Stack Overflow, so you can use this forum as well. And with that, I believe we're done with the announcements. And I would like to introduce you to our instructor today. Jerry Krause is a DevTech at NVIDIA, who is a guru in OpenACC and multi-GPU topics, among a lot of others. And he's working with the Jülich Supercomputer Center, helping them accelerate HPC applications. Jerry, you ready?
Yes, thanks for the introduction. And also welcome from me to everybody on the course. Thanks for joining. Yeah, I will talk about advanced multi-GPU programming with MPI and OpenACC. For those of you who have been joined the last online course, there's a little bit of overlap because I reintroduced some aspects of, give a very quick introduction to what MPI and what multi-GPU programming with MPI means in general, so that everybody can catch up. So let's get started. So MPI plus OpenACC programming is interesting for you because you probably want to program multiple GPUs in a cluster, distributed in this case over n nodes. Each node has one GPU, and if you want to use that cluster to solve a program coordinatively so that you reach the solution faster, you probably need to exchange messages at some point. So sending data from the GPU memory, for example, from node 0 to the memory of the GPU in node n-1. And if you know MPI and OpenACC already, that essentially really works as expected. You just call MPI send on the device on the buffer in the GPU of node 0 and MPI receive on the buffer in node n-1. For that, it's important that you use ACC host data use device, because per default, the OpenACC compiler would pass in the host representation, the host reference of a buffer and not the device buffer. So using that directive is important because in an OpenACC program, you're usually modifying the device reference, and therefore you would be communicating stale data if you send the device, the host representation. Okay, what's the agenda for today after this short introduction? So first, I want to explain by example how to use MPI for inter-GPU communication, including a very brief introduction to MPI. Then I will talk a little bit about how to debug and profile MPI plus OpenACC applications, touch on the multi-process service and how it can help to improve speed up when porting legacy MPI applications to OpenACC. And finally, how you can decrease parallel overhead and improve the scalability of your program. Okay, let's start with using MPI for inter-GPU communication. First, what is MPI? It stands for the Message Passing Interface, and this is standard to exchange data between processes via messages. It defines an API to exchange messages where we have different classes, point-to-point, for example, MPI send, MPI receive, or combined MPI send-receive operations, or also non-blocking versions, MPI I-send, I-receive. And besides that, also collective operations like MPI reduce or reduce, and so on. There exist multiple implementations, both open source and commercial, with bindings for C, C++, Fortran, Python, and so on. Just to name a few examples, OpenMPI, MVA-pitch, and MPitch. So how does an MPI code look like? So give a very brief skeleton. You first have to, of course, include the header defining the MPI API, MPI.h. Then you have to initialize before you can call any other routine from the MPI routine, you have to initialize the MPI library by calling MPI init. And corresponding to that, at the end of the program, you should clean up after yourself and call MPI finalize. Between that, you can do call all MPI routines to coordinate the work of all the participating processes. I want to highlight here two things that are usually called first because they are needed to identify the process in the set of processes participating in the run. So the first one is MPI comrank, which returns an ID from 0 till size -1 to the calling process so that it knows its unique ID within the set of processes. With a set of processes and can coordinate any communication. And the second one is MPI comsize, which returns how many processes are participating. Okay, I will explain by example how these values can be used later. Let's first take a look how this one is compiled and launched. So compiling is just done like with regular compilers, just that you need to set include paths and library paths correctly. And to ensure that, usually MPI implementation come with compiler wrapper, which in case of C is called MPI-CC, so you just use MPI-CC instead of your regular compiler and compile your program. Next thing is you need to launch multiple instances of your application so that you have actually many instances that can work in parallel. For that, MPI implementations provide so-called launchers, which are not always named the same. Often they're named MPI run or MPI exec. On SRM systems, you sometimes have to call srun. On Gray systems, you need AP run. And but they all usually have sometimes differently named. The most important argument, besides others, which are for fine-tuning process placement and are not covered in this talk, is the -np argument, which says how many instances I want to launch. So you just prefix your application with MPI run -np, in this case 4, to launch 4 instances, and then your application and arguments. And that will spawn 4 instances of your application to 4 nodes of your cluster, or to 1 node with 4 GPUs of your cluster, and sets the rank to 0 for the first one, to 1 for the second, and so on. Okay, so how does an MPI application look like? Let's take a look at an example. A JACOBI solver for the 2D Poisson equation on a rectangle with a given right-hand side, which has periodic boundary conditions. And to distribute the work across multiple GPUs, we do a domain decomposition with stripes. So as you can see on the right, we're dividing our domain in 4 smaller subdomains of the same size, and assign each domain to 1 GPU, and then exchange data between them via halo regions, which are shown in light green. Okay, let's first take a look at the single GPU JACOBI solver so that you're reminded or get an idea of what it does. So it executes a while loop till it's not converged, and in each iteration of the while loop, it executes one JACOBI step, which iterates over all interior points of the domain, and essentially calculates an average of the 4 neighboring points, writing to the variable a new. After that step, a new is copied to A, so that these two representations are swapped, and a new can be used as for the same purpose in the next iteration, and then the periodic boundary conditions are applied, which is essentially a copy of the last modified row to the top boundary, a copy of the first modified row to the bottom boundary, copy of the first interior column to the right boundary, and a copy of the last interior column to the left boundary, and then the next iteration is started. Okay, how can we do that with multiple GPUs? As said, we are dividing our domain in multiple stripes, and every GPU is then only working on the stripe assigned to it. In this case, the GPU currently looking in this case is starting at the row IY start and computes till the row IY end. Because each GPU only works on a subset, we now need, after copying A to A new, we need to exchange data so that information can propagate over the whole domain. And for that, each rank sends the last row it has modified to the top halo of the bottom boundary, to the top halo of the bottom boundary, and the top inner row it has modified to the bottom halo of the top neighbor. So these halo regions, thinking about each rank as a single GPU, these halo regions can be treated essentially as the boundaries, and the boundaries of the global domain are the real boundaries, and the boundaries in the inner domain are to exchange data between the GPUs and are called halos. Okay, how does this communication of halo values work with MPI? So let's take a look. First, as I already mentioned, it's important that because we are executing the solver completely on the GPU, so we are modifying the device representation of our field A. So it's important to use the Pragma ACC host data use device, so that always the device representation and not the host representation with stale data passed to MPI calls. And then in the first step, we call MPI send receive, which is a combined send and receive, and send the first modified row to our top neighbor and receive to our bottom halo from our bottom neighbor. In the second step, we receive our top halo from our top neighbor and send the last modified row to our bottom neighbor. If we do this now in a ring exchange, treating the neighbor of rank, the top neighbor of rank 0 being the last rank and the bottom neighbor of the last rank being rank 0, this will also automatically handle the periodic boundary conditions. Okay, that essentially explains how you can communicate data between GPUs. So you know how to compile an MPI program, how to start it, how to exchange data between GPUs. One thing you need to know in addition to that is how to handle GPU affinity, because if you're running on nodes with multiple GPUs, you have multiple MPI ranks running on each node, and they need to coordinate which MPI rank should use which GPUs, because otherwise they would just all use GPU 0, and you would oversubscribe GPU 0 and leave GPU 1, 2, and 3 idle. So to do this with OpenACC, I've protected that with preprocessor macros so that you still remain have a program that works without OpenACC. You query, in case you're using an NVIDIA device with separate memory and not, for example, the multi-core targets also supported by the OpenACC implementation by PGI. You query how many GPUs you have in a node, and then a simple assumption would be that you rely on ranks to be consecutively placed on each node. So that rank 0, if you start 4 ranks per node, that rank 0, 1, 2, and 3 are all placed on the same node, and rank 4, 5, 6, and 7 are placed on the next node, and so on. And then you can use a modulo operation of your rank by the number of GPUs to select the device you want to use by calling ACC set device num on that device num. An alternative to that would be to use environment variables provided by the MPI launcher. For example, the launcher of OpenMPI sets OMPI com world local rank, which is the ID of your MPI rank just within the node you're running on. So you could also just call A to I getEnv OMPI com world local rank to get the device num. Okay, I see there are some questions. Let me try to answer them now before jumping to the next question. So the first question is, can we use MPI and PGI Fortran along with OpenACC? Yes, of course. I'm presenting all the examples in C, C++ on the slides, but the homework is available in C, C++, and Fortran. And the concept is exactly the same. Just the syntax would be slightly different. Yeah, just what is needed with Fortran compared to OpenACC. Second question is, I'm familiar with MPI for multiple processors and threading for multi-core processors. And what are my thoughts on this? Yeah, that's actually when you compare MPI plus OpenMP parallel program, it's programming-wise, it's very similar to programming MPI plus OpenACC. The only you essentially start, in case of MPI plus OpenMP, you would start 1 MPI rank per CPU socket and then use as many OpenMP threads as the CPU socket has cores. In case of MPI plus OpenACC, you would start 1 MPI rank per OpenACC device and use OpenACC for the parallelization within the OpenACC device. Next question is, can we use MPI send receive inside compute regions? No, that's not possible. MPI is a host side API and can only be called from host code. So you can directly call send from and to GPU buffers, but the communication is handled by the CPU. And another question before I continue with the next session is, if an MPI node has multiple cores and a single GPU, should we use OpenMP for the cores and OpenACC for the GPU? You can. That's a very good question. You can do that. If it makes sense, really depends on your problem. The thing is that usually the performance of the CPU and the GPU is usually quite different, so you need to take care of load balancing, and usually that taking care of that adds some overhead, and if it pays off at a net effect, really depends on your applications. Oh, yeah, there's one more question coming in, which I can answer now before continuing. If all GPUs are installed on one computer, do we need to use MPI? No, you don't need to use MPI. You could also, for example, use OpenMP to start one CPU thread per GPU, or you can just call ACC set device num and switch and control all GPUs from a single device. However, you can use MPI also within a node, and so it works within a node and allows you to scale beyond the cluster. And furthermore, compared to the other two approaches, it has the advantage that you can transfer data directly between GPU buffers with GPU like peer-to-peer. This functionality is currently not available with the other approaches. There was a follow-up question on the OpenMP and OpenACC question for the course. Currently, it's not possible to build fat binaries with OpenACC for multi-core and GPU. But so each MPI rank, and even if each MPI rank would need to decide if it wants to use an OpenMP a GPU or the multi-core, and therefore you could use that with a fat binary by just launching 2 MPI ranks per node and then deciding which one uses which target. But still, you have the load balancing problem. Oh, there are more questions coming in, and so I think we can still answer them now. How do we know if we can use CUDA GPU-aware MPI, and if there's a runtime check, or a compile time check? Unfortunately, there's no standard way. However, OpenMPI defines a macro and a function you can call during runtime to check for CUDA awareness. For that, you have to include the MPI ext header. Okay, let me continue with debugging and profiling for MPI and OpenACC applications. So I want to introduce 3 tools which are relevant for MPI plus OpenACC development. One is CUDA-MEMCHECK, which is a memory correctness and checking tool like Valgrind. Then you can use the GPU debugger CUDA-GDB for OpenACC programs compiled with debug information. And furthermore, you can use NVProf or PGProf and the visual profiler to profile MPI plus OpenACC applications. Okay, let me start with memory checking with CUDA-MEMCHECK. So yeah, CUDA-MEMCHECK is a tool suite very similar to Valgrind's MEMCHECK, and it can be used in an MPI environment just straightforward. Just launch one CUDA-MEMCHECK instance per MPI rank with your application. So use MPI+OPENACC as a launcher for CUDA-MEMCHECK, which is used as a launcher for your application. This works, but usually produces quite some unreadable output because CUDA-MEMCHECK doesn't know about MPI, so every rank writes to standard out, and therefore the output of all processes is interleaved, which is hard to read. There's a solution to that by using environment variables provided by the MPI launchers, which is, in case of OpenMPI, OMPI COM world rank, and in case of MBA-pitch2, MV2 COM world rank. Another MPI might define a different, probably defines a different variable. For example, I've seen PMI rank being set. This environment variable contains is set differently for each instance and matches the rank in MPI COM world. So you can use that to pipe the output of CUDA-MEMCHECK to a named file. In case of CUDA-MEMCHECK, you have 2 options: --log file, which saves the textual output, and save, which saves the binary output, which you can later read in with CUDA-MEMCHECK. And then %q curly brackets and the environment variable will replace at runtime this expression with the value of the environment variable. So to give a short example, if you pass these variables, it will produce a log file for each rank. So I've started with 2 ranks, so I get a log file for 0, a binary file for 0, a log file for 1, and a binary file for 1. And the binary files I can read in with CUDA-MEMCHECK read, and then I get just the regular CUDA-MEMCHECK output identifying the issue in my MPI+OPENACC program. Okay, if this is helpful to identify a lot of errors, and hopefully you don't need to dig further, but if you need to, you can also use CUDA-GDB with MPI implementations. Just like you probably know how to use GDB in an MPI environment. For example, for smaller applications, you can just start an Xterm with a CUDA-GDB instance for every rank. This is, of course, not scalable because with if you imagine with 256 MPI ranks, having to manage 256 Xterm and CUDA-GDB instances probably not very good. So there are a few other options. First one is that you can attach to a running process. So you can do it programmatically by just inserting an infinite loop where you need to change a variable in the debugger and print the PID, the host name, and the rank just before entering an infinite loop, so that you can then just use CUDA-GDB to attach to the process. There are 2 more environment variables I want to mention. One is CUDA device waits on exception. If that's set to 1, a process will, if it hits, for example, out of bounds memory exception, it will not crash. It will halt and print a message containing the host name and the PID of the application so that you can use that to attach to it and inspect the state and hopefully identify the issue of your application. Furthermore, there is you can generate core dumps if you set CUDA enable core dump on exception to 1, and you can selectively decide to also create. It will always contain a GPU core dump, and you can selectively decide if it should also contain a CPU core dump, which might make sense to strip that off to save some space. The CPU core dump feature can be set with CUDA-ML CPU core dump on exception. And these core dumps then can be used for offline debugging and are helpful if you can't do live debugging because you need too many nodes or you can only submit jobs via a batch system or so on. You can also define the name of the core dump file, and then in CUDA-GDB, you can open them with target CUDA core to open just the GPU core dump, or with target core and then the core file of the CPU and the GPU to open both of them. To give an example of that, if you set that, you get the 2 files and can open them and then inspect the state of your program to identify the error. Besides this, there are also third-party tools with scalable debuggers, which you probably know from other MPI experience. There's the Alinea DDT debugger is GPU aware, and the RookWave Total View debugger is also GPU and OpenACC aware. Okay, now you know how to build to write an MPI+OPENACC program, and you know how to debug it, so you probably want to improve performance. So let's look into profiling MPI+OPENACC applications. Yeah, you can use the NVProf and NVVP for that. And just like with CUDA-GDB, you just start MPI run, use MPI run as a launcher for NVProf, which is used as a launcher for your application. Problem again here is that output would be interleaved, but you can use the same trick by using the environment variables OMPI, COM_WORLD_RANK for OpenMPI, and so on for others, to pass the output to to create one output file for each rank with the output profile option. With CUDA 7.5, we introduced something more, that you can also name the process and the context name shown in NVVP with the options -- process name, and then you pass in a string where the environment variable with a %q is also replaced with the rank and the where it is created for. Alternatives, you could also profile all processes on a node with the profile all processes option, or only save the textual output. Okay, doing that will create one MPI, and again starting with 2 MPI ranks, and it will create 2 files, one for each MPI rank, named with 0, which can be imported into NVVP with the import wizard selecting the multiple processes view, and then you see process MPI rank 0, process MPI rank 1, the context rank 0 running on a K80, context rank 1 running on a K80, and that they work in parallel, and you can see if there are load balancing issues and how the communication works. As with the debugging, there are also third-party tools, which, especially with regard to MPI profiling, are far more powerful. And are also CUDA-aware. I want to highlight here SCORP, which is a tracing framework, and Vampire, which allows to view these traces and the communication patterns and so on. Okay, before going to the next session, let's take a look if there are some questions. Okay, I think there's probably no unanswered questions. So let's continue with the multiprocess service. The multiprocess service is interesting for GPU acceleration of legacy MPI apps. So typically, a legacy application you might be working on is probably MPI parallel and might use a single or few threads per MPI ring, for example, with OpenMP. And so usually you would run with multiple MPI rings per node. And your GPU acceleration is in a proof of concept, or you just got started and you get a great speed up at kernel level, but your application performance misses expectations. So your performance might look like that. You have, with one rank, you have kind of this profile. You have a red serial part, a blue CPU parallel part, and a green GPU parallel part. If you scale that on multi-core CPU, the CPU parallel part and the GPU parallel part both scale with the number of CPU cores you use, so that you're getting a nice speed up. And if you go to the GPU, you can only use one MPI rank, and you see a significant speed up of the GPU parallel part, but you're slower than the CPU version because you're not scaling for the not GPU parallelized CPU parallel part. And the multiprocess service, MPS, or also known as Hyperq for MPI, enables you to just do that and just launch multiple MPI rings per GPU, so that the MPI rings share a GPU, and you can also benefit from the multi-GPU scaling and therefore also getting the full application speed up on a full node. So there are some other benefits of MPS that I want to highlight. First one is you can share a GPU also without MPS, which is not recommended, but you can do it. And every process will have its own context, and a GPU can only serve a single context at a time. So they would execute the kernels one after the other. So first the context from process A would execute the kernels, and then the kernels from process B would be executed. And between the two, we have a context switch. So even if even if the kernels are so small that they're not occupying the full GPU, this would happen. With MPS, the two processes are sharing a context on the GPU. We are the MPS daemon, and therefore the kernels of both processes can run concurrently if insufficient resources are available, speeding up the application. Furthermore, we don't have any context switch overhead. And to take a look at a case study, UMT, we, as already said, your small kernels of different MPI rings can run concurrently and increase GPU utilization. And also, you get overlap of copies of one MPI ring with compute of different MPI rings. So let's take a look at a few case studies and the effect on that. So what I did here is measured the speed up one get by sharing a GPU without MPS. So essentially, how much faster the application runs with using all CPU cores and sharing a GPU without MPS. And you see that for these applications, the speed up, depending on if they already support threading or not, is quite significant. If we add MPS and avoid the context switching overhead and allow overlap of work of different MPI ranks running on the same GPU, we get an additional speed up. So how can you use MPS? So you don't need to do any application modifications. You just need to start your application a little bit different. It's not limited to MPI implementations. So, and what you need to do is you just need to start multiple MPI rings per GPU. If you control the GPU affinity with a modulo operation like I have just shown, that will automatically then assign multiple MPI rings to a single GPU. And before that, spawn a MPS control daemon, which automatically spawns an MPS server when a CUDA application is started. So a typical setup would be to set the GPUs to exclusive process mode and then start the NVIDIA CUDA MPS control daemon. This is a manual setup. On many clusters, the administrator provide a different way to start up MPS. For example, we have job properties or so. One example is on Cray systems. You just have to set the environment variable Cray CUDA MPS to 1, and then MPS is automatically started for you. Okay, you can find more information about MPS on docs.nvidia.com/deploy/index.html. And I want to summarize that it's an easy path to get GPU acceleration for legacy applications. It enables overlapping of memory copies and compute between different MPI rings. But so you might think, oh, I want to always start that. But I would not recommend to do that because it adds some overhead if only a single rank is using a GPU. So it should be started selectively. Okay, I see there are no questions, so I'm continuing with the last part of today's lecture, decreasing parallel overhead. Taking the JACOBI solver I have used at the beginning and measuring the runtime for different problem sizes on 4 Tesla K80. We see that the runtime gets, of course, down with smaller problem sizes. And what I compared here is the with no overlap, the runtime with the ideal speed up we would expect with 4 Tesla K80, which, by the way, is 8 GPUs. And you see there's quite some gap, so which is caused by parallel overhead. We don't have load imbalances here, but we need to exchange halo data between the GPUs, which is something that is not necessary in a single GPU version. So how does it come from? So we essentially process our whole domain, then exchange data with our neighbors. So this MPI time is only done for multi-GPU runs. And we cannot avoid the communication because it's necessary, but we can lower the impact on the runtime by overlapping the time for the MPI communication with the processing of the whole domain. Because we only communicate the top row we have modified and the bottom row, so we could first process the parts of the domain we need to communicate with other processes, and start immediately after that start MPI communication, and in parallel to that then process the rest of the domain, which allows to overlap the MPI communication with processing on the GPU and therefore hides the communication time necessary. So how can this be expressed with OpenACC? So first we process the boundaries with an ACC kernel. Then we start asynchronously the processing of the inner domain. So the control immediately returns to the CPU after launching this kernel. And then we carry out synchronously the MPI communication. And at the end, wait for our asynchronously processing of the inner domain to finish. So that's the impact on the example application. You see that for the speedup is not that large for the very large grid because the relative runtime share for communication is not that large, but it increases it's quite significant if you look at smaller problem sizes where communication plays an important role. Okay, that is about hiding communication time. Another thing to decrease this parallel overhead is to lower the amount of data you need to exchange. And for the example I presented, we used horizontal stripes. And if we run with many processes, these domains get thinner and thinner. But the boundaries, the data we need to communicate across the boundaries stays the same. So I want to introduce different ways to do a domain decomposition. First one, I already said, is horizontal stripes or vertical stripes in 2D or planes in 3D, which minimizes the number of neighbors I need to communicate to. For example, we only need to, in 2D, each GPU needs to only compute with 2 other GPUs. And it can avoid non-contiguous halo exchange because we have in C, we have row major order, so the halo can be sent in one contiguous message. And in Fortran, we can use vertical stripes and can use the column major order to send the halos also in a contiguous message, which is, therefore, this is best for latency-bound problems. An alternative to this is using tiles or boxes in 3D and communicate. And then we need to communicate with up to 4 neighbors, or top, left, right, and bottom. And this strategy minimizes the surface to volume ratio, and has the downside that we need to communicate non-contiguous halos. So the columns in case of C and the rows in case of Fortran, and therefore we need to we have a little bit higher parallel overhead, which only pays off if the communication is actually bandwidth bound and we really gain something from communicating less. So how is the 2D domain decomposition applied to our multi-GPU JACOBI solver? Okay, we know not only dividing our domain in stripes, but in tiles. So we are computing from row AY start till row AY end, and furthermore also only from column AX start till IX end. Then do the same. One JACOBI step on these rows, copy A to A new, And now we need to exchange the halo with 4 neighbors. We need to send our last modified column to our right neighbor, our last modified row to our bottom neighbor, and so on. And then start the next iteration. Okay, besides computing, which is the start and the end row, and an important thing is how to handling tile GPU MPI rank affinity, because we now have, taking example now by a 3x3 tile domain decomposition, and so we would, to calculate our left and right neighbors and the top and bottom neighbors, we would like to have two-dimensional ranks, like 0, 0, 0, 1, 0, 2, and so on. However, MPI com rank and com size only gives us 1, 2, 3, 4, 5, 6, 7, 8. And so how do we map these two? The MPI standard provides Cartesian communicators for that, which you can use with create with MPI card create and use with MPI card shift. I don't want to go into the details of that, but rather explain how you can do this manually, so that you can understand what's going on. So we have our 3x3 tile domain decomposition and start 9 MPI ranks. So first thing we do is calculating our number of ranks in X and Y direction. So the size in X direction is in this case hard-coded, but usually would be provided by a command line argument to your application. So we know how many ranks we want to have per row, per set of rows. And from that, we can just divide our size, our global number of ranks by the number of ranks per row to get the number of ranks per column. And then just insert an asterisk to check that there are no rounding errors because we have passed wrong arguments. After that, we want to map our 1D MPI rank to 2D MPI ranks. And that we can just do with a modulo operation by doing a rank modulo size X to get the X coordinate of the tile we are responsible for, and with the divide operation of our global rank to get the Y coordinate of the tile we are responsible for. Okay, now we have the two-dimensional ranks so that we can compute which rows and columns we are responsible for and which are our left and right neighbors. Now we need to map that back to global MPI ranks so that we can use it in MPI communication. And for that, we first, to give an example, the neighbors in Y direction, we, if we want to get our left neighbor, we take our rank -1. Unless we are the first rank in that row, then we take the last rank on that row. And the right neighbor is the same. We take our rank in Y direction +1. Unless we are the last one, then we take rank 0 in that row as our right neighbor. Mapping that back to 1D MPI ranks can be done with the following expression by just calculating our index in Y direction, multiply it by the width, and adding our X rank, and the same, of course, for the right neighbor. And then we can use these to communicate with our left and right neighbors. Since data is now non-contiguous and sending very small messages with MPI is inefficient, we first want to gather our non-contiguous data into a contiguous buffer, which we then can send to the neighbors which are requiring them, and receive to contiguous data buffer, so that we can scatter that to our non-contiguous data. again, here doing that manually, there's an alternative by using MPI data types, and using them might be more efficient because the MPI implementation could do can also do this gathering and scattering from you, even in GPU memory, and can embed that in its internal pipelines, running more efficient. Okay, with that, I want to close and happy to take more questions. I want to make you aware of the homework, which you can access over Quick Labs. Go to developer.nvidia.com quick lab sign up. Use the OpenACC promo code to register and get a free access. After you receive the confirmation email, you get access instructions, and with that, take the Advanced Multi GPU Programming with MPI and OpenACC Lab. Okay, let me look at questions. There was one question: is OpenACC supported on Azure AWS? So OpenACC requires an OpenACC compiler. So if you have one, if you install one on your Azure AWS instance, you can use OpenACC there. Actually, the Quick Lab is running on an AWS cloud instance, and we have the OpenACC compiler running there, so you can even try that in the homework. On slide 44, there's a question on slide 44, and on the chart, N represents a number of processors or multiple core GPU. N represents a number of, on this slide, N represents a number of MPI ranks and corresponds to the number of CPU cores used. So N1 means one single-threaded MPI rank running on one CPU core. N2 means 2 single-threaded MPI ranks running on 2 CPU cores. Then there's one more question. Do all these examples assume that all the data can fit on the GPU simultaneously? Yes, the problem is assumed to fit in the aggregate GPU memory of all participating GPUs. Then there's a question with if the PGI Fortran compiler can be used with MPI run and MPICC. Yes, the PGI Fortran compiler can be used with MPI. You would also use MPI run to start your application, but you would use the MPI F90 compiler wrapper instead of the MPICC compiler wrapper to access the Fortran compiler. There's one more question. Is it straightforward to stream data to the GPU with OpenACC? Probably a follow-up to the question if the data needs to fit into the memory of the GPU. Yes, you can do that with async clauses and for asynchronous data transfers. This topic was covered in the class number 4 of the last OpenACC course. So if you're interested in that, you could either watch a recording of that or take the lab covering that topic. Another follow-up question on that is, if streaming works with MPS? Yes, streaming also works with MPS. You just have to consider that if you share a GPU with multiple MPI rings, there are just more processes competing for GPU resources. So if one GPU resources is occupying the copy engine to move data from the CPU to the GPU, it's blocked for the others. Then there's a question why MPS is for legacy MPI implementation. So it can be it's meant for. I highlighted that it is for legacy MPI applications, because with a legacy MPI application, you probably have started to accelerate the few most important routines, but not all of them. So you have the effect shown on the slide, on slide 44, that you're getting speed up for these routines, but not for the other routines. So, and then MPS enables you to get an application speed up. In general, if you continue, usually you would also parallelize the CPU parallel part on the GPU, and therefore all of that would run on the GPU, and then you would no longer use MPS and just start one MPI rank per GPU. There's a question if its operations run on a GTX 960 and a GTX 730 on Linux, on a Core i7 on Linux. Yes, however, you would likely get load balancing issues, and compared to Tesla, you can't, the CUDA-MEMCHECK will not use GPU direct peer-to-peer transparently for you. Then there was a question, which PGI compiler version did I use, and if there's a difference between recent versions. For the code presented here, I'm not aware of any major differences between the recent versions, and I used version 16.3 for that. Okay, since there was a question on using that on GeForce, I want to jump to an implementation detail of CUDA-aware MPI, explaining what benefit you will get from using a CUDA-aware MPI, in addition to the ease of use by just passing in device representations. Okay, so first thing I want to shortly highlight why it works, CUDA-aware MPI, and the enabling technology for that is unified virtual addressing, because unified virtual addressing puts all the memory of the CPU and the GPU in one large single address space, so that you can identify where a pointer points to from its values. If you would have no unified virtual addressing, you would have two address spaces for the CPU and the GPU, and you could have one pointer value which is valid on the GPU and on the CPU, but points to different memories. With unified virtual addressing, for example, a library can query the pointer if it points to GPU memory or to CPU memory, and depending on the physical memory location, it can take different execution paths. So in case of MPI, if it gets a GPU memory, it can start a host staging pipeline or use a GPU direct path, which I will introduce in a second, to transfer the data and use some other methods to move the data from one rank to the other if it is a host pointer. A requirement for that is a device with compute capability 2.0 and a 64-bit application, which should be pretty much everything today. Okay, that's the enabling technology for CUDA-aware MPI. But another benefit, so how you can use it, and I want to highlight some acceleration technologies which you might have heard about, GPU Direct, which CUDA-aware MPI will transparently use for you to speed up your inter-GPU communication. First one is GPU Direct for accelerated communication with network and storage devices. That allows that an InfiniBand adapter shares a pinned system memory buffer with the GPU, so that a DMA transfer from the GPU can directly go to a buffer which can also be used for RDMA transfers to a remote node. Without this technology, you would need to have one DMA-able buffer for the GPU and one for the InfiniBand adapter, and therefore had one intermediate copy within system memory. This one is pretty much available on all systems supporting GPU Direct. Second one is GPU Direct peer-to-peer, which allows to directly transfer data from one GPU to another GPU if they are if they are connected to the same PCI Express root complex. So without GPU Direct peer-to-peer, you would need the data would first need to be copied from one GPU to system memory, and then from there to GPU 1. With GPU Direct peer-to-peer, this can be avoided, and it's directly sent over PCI Express bus. The third one, last one, is GPU Direct support for RDMA, which allows to do the same as GPU Direct peer-to-peer by sending data directly from GPU memory to an InfiniBand adapter, avoiding the staging through system memory and significantly reducing latency. Okay, what does it mean for does a CUDA-aware MPI use that? For that, I want to show you a short example, which says that MPI rank 0 does an MPI send from a GPU buffer, and MPI rank 1 does an MPI receive to a GPU buffer. And this shows how how OpenACC or CUDA plus MPI works in principle. Depending on the MPI implementation you use, the message size, system setup, for example, if GPU Direct RDMA or GPU Direct peer-to-peer is available, the situation might be different. I'm looking here at 2 GPUs and 2 nodes. So let's start with the best of both worlds if we have support for GPU Direct RDMA. If we call an MPI send, the data is directly sent via the network and from the network to the destination GPU. So any possibly needed host staging buffers are avoided. The MPI implementation might decide to implement that in a small pipeline, and therefore, in this case, for example, transferring it in 4 smaller chunks, but leading to a quite short communication time. In contrast to this, if we would use a regular MPI to send GPU memory from one GPU to the other, we first need to copy, which would be ACC update host from the GPU to the host memory. Because this copy happens with DMA transfers, so that will also involve intermediate copy to a driver-managed staging or OpenACC runtime-managed staging buffer until we have transferred all the data to application-managed, the application buffer on the host. Then this one can be sent with MPI over the network, which might involve a RDMA-able pinned buffer managed by the InfiniBand adapter, sent over the network. We have also, again, the RDMA-enabled buffer, possibly the host side buffer, then the DMA buffer managed by the CUDA driver or the OpenACC runtime, and then the DMA to the GPU. So this involves quite a few more steps, but more importantly, after the host to device transfer, the pipeline is stalled before the MPI send receive pipeline can start, and it's again stalled after the MPI send receive pipeline before the host to device pipeline can be stalled. So one last case, if we have a CUDA-aware MPI but no GPU Direct, we can pass a GPU pointer to the MPI directly, and then we avoid first of all, we avoid the staging to the application managed host buffer on the sender side and the receiver side. But more importantly, everything is executed in one pipeline, so we avoid the pipeline stalls. So what does that mean for performance? Looking at the micro benchmarks, a ping pong benchmark for different message sizes, we see that with the regular MPI and manual host staging, we only need about reach about half the network bandwidth, and with a CUDA-MEMCHEK, we can saturate the network bandwidth. Furthermore, if GPU-Direct RDMA is enabled, we get a far lower latency for GPU to GPU communication. Okay, with that, I'm happy to take more questions, and if there are none, I'm taking over to Julia again. There's a question, slide 92, if it refers to, this is run on a Tesla K40, so it was connected with PCI Express 3. However, the Mellanox adapter is also only connected with 8 lanes of PCI Express 3, and also because it's sufficient to saturate the FDR IB bandwidth. So it's using PCI Express 3 for the GPU, but we are not seeing the PCI Express 3 bandwidth because we are limited by the network bandwidth.
Okay, great. Thanks a lot, Jerry. Let's go back to our questions. Sorry. Okay, so please submit the questions through your Q&A pod. We still have time. And okay, there is one more question about CUDA-MEMCHEK. Okay, you can see it here.
Yeah. Yes, CUDA-MEMCHEK uses GPU-Direct RDMA, GPU-Direct automatically. So it detects if, in case of GPU-Direct peer-to-peer, it does that always by detecting if a GPU-Direct peer-to-peer path is available, and if so, uses GPU-Direct peer-to-peer. In case of GPU-Direct RDMA, it's a little bit dependent on the MPI implementation you're using. For example, in MBA pitch, you need to enable GPU-Direct RDMA with an environment variable.
Great, thanks. And let me do a couple announcements while people are submitting more questions. So again, one more time, just a reminder, this is the final session of our OpenACC course, of the advanced OpenACC course. We're going to be doing more courses going forward, and we'll keep you updated. If you have any questions, there are a lot of resources for you available. For example, you can go to OpenACC.org. There are a lot of materials out there. We are also posting a lot on the Stack Overflow. You also have an email, openacc@nvidia.com, for your questions. If you have any ideas, any topics that you're interested in to cover next time, please let us know as well. You also can download the OpenACC Toolkit, which is free for academia. It's a free license that works on the workstation. You're welcome to download it. If you're in industry, you still have an option to download it for free and use it free for 3 months. If you're interested in teaching a similar course, please contact me. We will help you out and give you more resources and materials to do so. Okay, let me check if there are more questions. Okay, Jerry, there's one question about, again, CUDA-MEMCHEK and GPU-Direct, or you already answered that. Never mind. Okay, let's see if there are more questions in the last couple minutes, and if not, we're going to wrap it up. And another resource for you guys is Exceed is actually in a partnership with Pittsburgh Supercomputing Center. They are performing OpenACC workshops, and it happens 3 times a year. And the next one will be mid-June, and it will be OpenMP and OpenACC combined. It's a 3-day boot camp. Again, you're welcome to join. Anyone is free to join. They don't have any limitations, I believe, and this workshop is designed to work on multiple sites. So they have about 12 or 13 different sites where people can attend the workshop live. Okay, with that said, I believe we will wrap it up. Thanks a lot for joining. Really appreciate all your questions and attendance. We're really happy to see that this is something helpful that we're doing. And one more time, there is a link for their homework. And don't forget to register to get the free credits to use the labs. If you don't have enough, please send us email. We will be happy to give you more credits to complete the homework. Thanks a lot for joining. Recording will be available later this week. Thanks again, and see you next time.